Good evening everyone. Good evening. I welcome you all again to the JEE Enthuse. Hope all of you are doing great, having the good time at home. Well, people, if I'm audible and visible to everyone, let me know in the chat box with the thumbs up. Let me know in the chat box with the thumbs up if I'm audible and visible to every single guy right here. Yes, walaikum salam everyone, walaikum salam. Yes, let me know in the chat box if I'm audible and visible to every single guy right here. Good evening, guys. Good evening. Welcome to the session, guys. Welcome to the session. Yes. Wonderful. So, people, as you all must be knowing, today we are going to do the part 2 of the mole concept. Yes. And the part 1 of the mole concept was done on last Monday, if you remember. In the last Monday's part 1 of the mole concept, we talked about the basic terminologies related to the mole concept. We did a lot of questions. We talked about limiting reagent. Yes. And today we are going to start few more topics, which include your percentage yield, percentage purity. Yes. It includes the mixture analysis, concentration terms. Everything will get discussed over here in the tonight's session, right? Walaikum salam everyone. Walaikum salam. Welcome, guys. Welcome to the session. Welcome to the session. Alright, guys, so before starting the session, let me introduce myself. As you all must be knowing now, my name is Wassim and I'm your chemistry master teacher right here. Yes. So, people, talking about the schedule of the week, which I'll be following throughout on this channel in this week, let me tell you guys, we are going to continue with something called as, we are done with this topic, solid state Menti quiz I took at 5:30 today. Yes, right now I'm going to do the marathon series on mole concept, right? And people, on Wednesday, I'll be doing the most expected JEE questions from the chapters thermodynamics, states of matter, redox reactions, okay? And this is valid for the ones who are going to write your JEE in 2021, right? And people, on Thursday, there will be part 2 of the chemical kinetics, and at the same time on Friday, there will be most expected JEE questions from the chapter chemical equilibrium, ionic equilibrium, and the mole concept. And people, at the same time on Saturday, we are going to do the chemical kinetics part 3, yes? No, Kirito, there won't be any class tomorrow, bro. Tomorrow I won't be taking any session, yeah? Because tomorrow I'll be taking a marathon series on NEET Lead channel, yeah? Right? Okay, so people, for the ones who have not liked the video yet, do like the video, share and subscribe the channel at the same time so that everyone gets benefited out of these sessions, right? So do it right now, yes? Okay, walaikum salam everyone, walaikum salam. Okay. So guys, before starting the session, I need to give you the brief introduction about the Vedantu JEE Pro subscription. What all benefits you guys are going to get if you'll enroll yourself in this Pro subscription. Let me tell you, you guys are going to get 5,000 plus hours of live online teaching. Regular tests and assignments will be provided to you, which contains more than 10,000 questions. We have got 20 plus teachers with 5 plus years of experience who will be training you personally for the upcoming JEE 2021 as well as 2022. And at the same time, you have got the option to learn either in English or in Hindi. It's completely your wish to select the language, get trained by the master teachers of Vedantu, right, in English or in Hindi, yeah? Okay, and people, at the same time, we are going to cover everything over here, which includes your micro as well as crash course. Yes. Now, guys, for the ones who are going to write your JEE in 2021, we have come up with 3 different plans, as you all can see. On every plan right here, we have got 20% off. The first plan, which is the 1-month plan, after the 20% off, you guys are just getting it for 6K. 3-month plan, 6-month plan, after the 20% off, you guys are just getting it for 16.8 and 31.2K respectively. And all these plans are valid for the ones who are going to appear in JEE in 2021. Yes. So people, for the ones who are going to write your JEE in 2022, again, we have come up with 4 different plans. On every plan right here, we have got 20% off, as you all can see right here. Yes, 1-month plan, 3-month plan, 6-month plan, and 12-month plan. After the 20% off, you guys are just getting it for 4K, 10.8K, 19.2K, and 33.6K respectively. Yes, and all these plans are valid for the ones who are going to write your JEE in 2022. Yes, so people, for the droppers, again, we have come up with 3 different plans, as you all can see. 1 month, 3 months, 6-month plan. After the 20% off, you guys are just getting it for 7.2K, 20.4K, and 40.8K respectively. And all these plans are valid for the ones who are going to appear in the JEE in 2021, who are the droppers right here. Yes? Okay. So people, how to get enrolled in it, how to get these pro subscriptions, let me tell you, there's a link in the description box of the video. I want you guys to click on that link, use the coupon code as WBPRO. On using this coupon code of WBPRO, you guys are going to get 20% off right here on whatever plan you're selecting for yourself, right? Okay, so people, let me know in the chat box if you guys are super duper excited for this session or not. Let me know in the chat box if you guys are super duper excited for this session or not. Shahid, well, it's not confirmed yet. You'll be getting the data tomorrow. Yes. Yes. Okay, so people, this is the marathon session series which we take every week. On Thursdays, you have got it with the Shimon sir in mathematics. On Fridays, you have got it with Shreya sir on physics. And on Mondays, you have the marathon series with me right here in this channel. Yeah. Okay, so people, let's get started with the part second of marathon mole concept right here. Yes. Yes. Okay. So let's get started with something called as percentage yield of the reaction. Okay, what is this percentage yield of the reaction all about, right? I'm just giving you a small theoretical part of it, then I'll be showing you its application in the form of problems, right? Understand properly what I'll say. Understand properly what I'll say. Let me tell you guys, percentage yield, how do we define it? It's defined as the experimental amount divided by expected amount multiplied by 100. This is the simplest formula by means of which we can calculate the percentage yield of any reaction right here. Now the point is, what is this experimental amount? What is this expected amount? What these amounts are all about? Let's get to know about these amounts a bit more in detail, okay? First of all, I'll be giving you one analogy by means of which you'll be getting to know what this experimental amount is all about, what this expected amount is all about. Let's get to know about it in detail, okay? Let me give you the analogy first, okay? If you remember, I always give this analogy when I teach the percentage yield, yeah? For example, guys, let's say I need to get one scanner. Let's say I need to get one scanner, yes? Let's say I need to get some scanner from the market. Let's assume that, okay? And I went to the shopkeeper and shopkeeper was like, for example, the scanner is giving me 50 pages per minute, yes? 50 pages per minute. Shopkeeper told me the scanner is going to give you 50 pages per minute. When I took the scanner home, it was only giving me 25 pages per minute, yes? So can I say this is something which I was expecting? Yes, this is something which I was expecting, that the scanner will give me 50 pages per minute. But when I actually checked this scanner at home, it was only giving me 25 pages per minute. Yeah. So can I say this is something which I was expecting? This is something which I was expecting. So should I be calling this amount as the expected amount? Absolutely, I'll be calling this as the expected amount. At the same time, this is something which I observed actually. So I'll be calling this amount as the experimental amount right here. I'll be calling it as the experimental amount right here. And in order to calculate the percentage yield, we should know both the things. One is your experimental amount. Another one is expected amount. I just have to divide the two, multiply by 100, I'll be getting the percentage yield. Yes, in order to calculate the percentage yield of the printer, how will I be doing that? I'll be simply writing something like this: percentage yield of the printer. It's going to be equal to experimental amount, it's going to be 25, divided by expected amount, it's going to be 50, multiplied by 100, the value is going to come as 50 right here. So this 50% is the yield of this printer right here. Now the point is, how do we link this percentage yield with our problems, with our questions right here, okay? So for that, I'll be directly starting with one question by means of which you'll get the clear-cut idea of where this percentage yield is used and how this percentage yield is used, yes? So people, something which you'll expect that I'll be calling as the expected amount. Something which will be experimentally observed, that's what I'll be calling as the experimental amount. Once you get the experimental amount, expected amount, you just divide the two amounts and multiply by 100, you get something called as the percentage yield of the reaction. Let's get to know about this in proper right here in the form of questions. Yes? See guys, the first question which is on your screen right here. As you all can see, on heating 40 grams of calcium carbonate, 20 grams of calcium oxide was obtained. This is something which is experimentally observed in the laboratory, that when you are heating 40 grams of calcium carbonate, 20 grams of calcium oxide is actually obtained. This is something which is actually obtained. This is something which has been observed in the laboratory. So I should be calling this amount as the experimental amount right here. Absolutely, yeah. Understand what I'll say. Understand what I'll say. On heating 40 grams of calcium carbonate, 20 grams of calcium oxide was obtained. This is something which has been observed experimentally in the laboratory, right? So I'll be calling these 20 grams as the experimental amount right here, right? Now guys, we know in order to calculate the percentage yield, we should know two things. One is your experimental amount, one is your expected amount. You just have to divide the two, multiplied by 100, you'll be getting the percentage yield of the reaction. Now guys, this is something which is given to me as per the question, and this is something which has been observed experimentally. I'll be calling this as the experimental amount. Now I need to get the expected amount. The point is, how do I get this expected amount? The expected amount I will be getting by using the stoichiometry of the reaction. Understand how properly. See guys, what I'm doing right here is I have got calcium carbonate solid and I'm heating this calcium carbonate. What it's going to get converted to, it will get converted to calcium oxide. At the same time, it will liberate some carbon dioxide gas at the same time. Yeah. Now guys, understand, is the reaction balanced right here? Absolutely the reaction is balanced. Absolutely the reaction is balanced. Yes. How many grams of calcium carbonate do we have? We have got 40 grams. Yes, we have got 40 grams of calcium carbonate right here. Okay. Now people, if I use the stoichiometry by using the mass method, how will I be doing that? Understand. If I ask you what is the molar mass of calcium carbonate, you'll simply say 100 grams. Can I say 100 grams is the mass of 1 mole of calcium carbonate? Absolutely. I can say mass of 1 mole of calcium carbonate right here is going to be simply as 100 grams, right? Similarly guys, what about the molar mass of calcium oxide? It's simply going to be 56 grams. So I will say 56 grams is the mass of 1 mole of calcium oxide. So I'm writing 56 grams right here. Yes. Yes. Now guys, understand properly. I can say 100 grams of calcium carbonate should give me 56 grams of calcium oxide. I'm using the term should, okay? 100 grams of calcium carbonate should give me 56 grams of calcium oxide as per the stoichiometry of the reaction. Can I say 1 gram of calcium carbonate should give me 56 divided by 100 grams of calcium oxide? Yes. But people, do I have only 1 gram of calcium carbonate or I have 40 grams of calcium carbonate? I have definitely 40 grams of calcium carbonate. So can I say 40 grams of calcium carbonate should give me 56 divided by 100 multiplied by 40 grams of calcium oxide right here. And people, when you will calculate this value will come out to be 22.4 grams, something like this. Yes, 22.4 grams of calcium oxide. Now the point is, what is this thing which I calculated right here? Understand. See guys, this is something which is given to me in the question that on heating 40 grams of calcium carbonate, 20 grams of calcium oxide is actually experimentally obtained. Yes. Now I use the term stoichiometry, I use the method stoichiometry by means of which I got to know from 40 grams of calcium carbonate, I should have got 22.4 grams of calcium oxide. So can I say this is something which I was expecting? I'll be calling this amount as the expected amount, and this is something which is experimentally observed. I'll be calling this amount as experimental amount. Now people, in order to calculate the percentage yield of the reaction, I wanted two things. One was your expected amount, one was your experimental amount. I will be simply calculating the percentage yield. Yeah. Simply, I'll be writing the percentage yield formula like this. I'll be writing percentage yield is equal to experimentally observed amount, which is 20, expected amount, which is 22.4, multiplied by 100. Can I say this value will be around 89%? So I can say yield of the reaction is 89% right here, which you can easily get it over here. Yes, this was the first question which we did by using the concept of percentage yield. Yes, let's try to do a few more questions by means of which the concept will get damn clear to you. Yeah, understand what I'll say. See guys, this is one more question which I have on your screen. Have a look on it. See guys, 1.12 grams of calcium oxide is reacted with excess of HCl and 1.776 grams of CaCl2 is formed. This has been observed experimentally that when 1.12 grams of calcium oxide is reacted with excess of HCl, you get something as 1.776 grams of CaCl2. This is something which has been experimentally observed. Yeah. What is the percentage yield of the reaction? So people, I'm given with the experimental amount. Remember, experimental amount will be always given in the question. Yeah. I'm given with the experimental amount. Now, in order to calculate the yield of the reaction, I should know what is the expected amount. Yes, I'm given with experimental amount. Now, I'll be using stoichiometry, by means of which I'll get to know what is the expected amount. And once I get to know the expected amount and experimental amount, I just have to divide the two, multiplied by 100. I'll be simply getting the percentage yield of the reaction. Yes. Now, guys, let's try to approach it. See. First of all, is the reaction balanced? Yes, the reaction is balanced. Yes. Understand what I'll say. Calcium oxide, guys. What is the molar mass of calcium oxide, as you all must be knowing? What is the molar mass of calcium oxide? I can say 56 grams is the molar mass of calcium oxide. Can I say 56 grams is the mass of 1 mole of calcium oxide? And right here, I have got 1 mole of calcium oxide only. Yes. So mass of 1 mole of calcium oxide is going to be 56 grams, right? Now guys, at the same time, if I ask you to calculate the molar mass of CaCl2, it's going to be 111 grams. Or I can say mass of 1 mole of CaCl2 will be 111 grams. Yes. Now guys, can I simply say something like this? Can I say 56 grams of calcium oxide? 56 grams of calcium oxide should give 111 grams of CaCl2. Yes. 56 grams of calcium oxide should give 111 grams of CaCl2. Can I say 1 gram of calcium oxide should give me 111 divided by 56 grams of CaCl2? But people, do I have only 1 gram of calcium oxide, or I have 1.12 grams of calcium oxide? I have got 1.12 grams of calcium oxide. So can I say 1.12 grams of calcium oxide should give me 111 divided by 56 multiplied by 1.12 grams of CaCl2 right here. Yes. So people, what is this value coming out to be? This value will come out to be as 2.2 grams. So I was expecting by means of stoichiometry that 1.12 grams of calcium oxide to give me 2.2 grams of CaCl2. I was expecting right here 1.12 grams of CaO to give 2.2 grams of CaCl2. But is it actually giving 2.2 grams of CaCl2? No way. Experimentally, it's observed that only 1.776 grams of CaCl2 is produced. Yes. So people, can I say this is something which I was expecting by means of stoichiometry? So I'll be calling this as the expected amount. People, I got to know the expected amount. Can I say this is what I call as the experimental amount, and I got expected as well as experimental amount. I can simply calculate the yield of the reaction. I can do that. I can simply write something like this. I'll be writing percentage yield of the reaction will be equal to experimental amount, which is 1.776 divided by expected amount, which is 2.2 multiplied by 100. Just calculate its value, guys. Absolutely, it's going to be 80% right here. Can I say 80% is going to be the yield of the reaction? Absolutely, I can say that. Yeah. Absolutely, I can say that. Yeah. 80% is going to be the yield of the reaction. Yeah. So I was expecting 2.2 grams of CaCl2 to get obtained, but actually only 1.776 grams of CaCl2 is obtained. So this is something which is experimentally observed. This is something which I was expecting through the stoichiometry. Yes, this is something which I was expecting through the stoichiometry. So people, this is what I call as expected amount. This is what I call as experimental amount. I have both the amounts. I can simply use the formula which I did right here and calculated the percentage yield of the reaction. Yes, very, very simple, right? Now guys, let's try to do one more question by means of which the concept will get again damn clear to you. Yes, understand what I'll say. See guys, 15.6 grams sample of benzene. 15.6 grams sample of benzene, yes, is mixed with excess of HNO3 in presence of H2SO4, and 18 grams of nitrobenzene is obtained. 18 grams of nitrobenzene is obtained. So actually it has been observed practically, experimentally it has been observed that when 15.6 grams of benzene is reacted with HNO3, you get 18 grams of nitrobenzene. Yes. So this is something which has been seen experimentally. Yes, this is something which has been seen experimentally, that when 15.6 grams of benzene reacts with HNO3 in presence of H2SO4, it actually leads to the formation of 18 grams of nitrobenzene. Yes. So people, should I be calling this as experimental amount? This is something which has been observed experimentally. So I'll be calling this as experimental amount. Yes. So people, you got the experimental amount. Now, in order to calculate the yield of the reaction, I can calculate only yield of the reaction if I know two values. One is experimental, one is expected. Yes, since I have the experimental amount, now I need the expected amount. Which I'll be getting to know by means of stoichiometry, right? Understand what I'll say. People, is the reaction balanced right here? Absolutely, the reaction is balanced. If I ask you what is the molar mass of benzene right here, you'll simply say 78 grams. Can I say 78 grams is the mass of 1 mole of benzene? Absolutely, right? So people, if I ask you what is the molar mass of nitrobenzene right here, let's calculate it. It's going to be 77 plus 14 plus 32. It's going to be 4, 2, 6, 7, 6, 13, 3, 7, 1, 8, 9, so it's going to be 123. So molar mass of C6H5NO2 is going to be 123 grams, or I can simply say mass of 1 mole of nitrobenzene is going to be 123 grams right here. So can I say by using stoichiometry that 78 grams of benzene should give me 123 grams of nitrobenzene? So can I say something like this? 1 gram of benzene should give me 123 divided by 78 grams of nitrobenzene. But people, do I actually have 1 gram of benzene, or I have 15.6 grams? Yes, from 15.6 grams, I was expecting the nitrobenzene to get formed like this. Yes, this is the amount of nitrobenzene which I was expecting to get formed. Yes, this is the amount of nitrobenzene which I was expecting to get formed by means of stoichiometry. Yes, yes, very, very, very simple. Simple, guys. Understand properly what I'm saying. 15.6 grams, experimentally it has been observed when 15.6 grams of benzene reacts with HNO3, it gives 18 grams of nitrobenzene. It gives 18 grams of nitrobenzene. Yes, it gives 18 grams of nitrobenzene. Absolutely. So this is something which has been observed experimentally, right? Now, in order to calculate yield of the reaction, I should know two things. One, that is the experimental amount. Number two, that is the expected amount. Once you get to know both the things, you can calculate the yield of the reaction, right? Right? So from stoichiometry, I'm going to get the expected amount right here. Correct? So I can simply say 78 grams should give 123 grams of nitrobenzene. 1 gram of benzene should give this much of nitrobenzene. So this much of benzene should give this much of nitrobenzene. So this value will be approximately 24.5 grams. So people, 24.5 grams of nitrobenzene I was expecting to get formed. Right? Now guys, so this is something which I was expecting, so I'll be calling this as expected amount. Once you get the expected amount, once you get the experimental amount, you can easily calculate the yield of the reaction. I can say simply percentage yield of the reaction is going to be experimental amount. How much that is? That is 18 grams divided by expected amount, which will be around 24.5 multiplied by 100. So people, just get the value. That is going to give you the percentage yield of the reaction. Yes? Exactly, it's going to be around 73.1%. This is going to be the yield of the reaction which we were supposed to calculate right here. Yes, absolutely. Correct? Correct? Yes? Okay. So people, Kuldeep, you can do one thing. You can take the video a little back. It will be automatically a replay, bro. Just take the video a little back. It will be automatically a replay. Right? Okay. Let's move on, guys. Let's move on. And this is one more question which I have right here. A very, very simple question it is. Just use the concept, get the question done, you're done. Yeah? Understand properly. On heating 150 grams of calcium carbonate, what mass of calcium oxide is actually produced, right? The yield of the reaction is given to me as 75%. Yes. Yes. Now guys, see what I'll be doing. Right here. If I ask you what is the molar mass of calcium carbonate, it's going to be 100 grams. Or I can say mass of 1 mole of calcium carbonate is going to be 100 grams, right? People, What is the molar mass of calcium oxide? It is 56 grams. So mass of 1 mole of calcium oxide is going to be 56 grams, right? So people, by using stoichiometry, can I say 100 grams of calcium carbonate should give me 56 grams of calcium oxide? So people, 1 gram of calcium carbonate should give me 56 divided by 100 grams of calcium oxide. Yes. So people, I have got 150 grams of calcium carbonate. So 150 grams of calcium carbonate should give me 56 divided by 100 multiplied by 150 grams of calcium oxide. So as per stoichiometry, I got to know that 150 grams of calcium carbonate should give me this much amount of calcium oxide. Yes. So people, if the yield of the reaction was 100%, then whatever was my expected amount, same would have been the experimental amount, but the yield of the reaction is not 100%, yield of the reaction is 75, yeah? Yield of the reaction is 75%. So I can say whatever is my expected amount, only 75% of this expected amount will actually get formed. Yes. So I can say mass of calcium oxide which actually gets formed, that is going to be 75% of the expected amount. That's going to be 75% of the expected amount. Yes. 75% of the expected amount. Very simple. So isn't it going to be 75 divided by 100 multiplied by, what is the expected amount? Expected amount is simply 56 divided by 100 multiplied by 150 grams. Just calculate this value. This much amount, this much grams of calcium oxide will be actually getting formed through this reaction right here. Yes. Very, very, very simple it was, right? So people, from here I got the expected amount. So from stoichiometry I got to know from 150 grams this much amount of calcium oxide should get formed, but 75% of the expected amount is actually getting formed, right? Right? Yes. Very, very, very simple. Correct? Absolutely uncharted. It's going to be 63 grams. Is that? Okay. Let's keep that as the answer. 63 grams of calcium oxide right here is actually getting formed. Tesla, no way. How come it can go beyond 100, bro? Okay, let's move on, guys. Let's move on. And let's talk about something called as percentage purity. First of all, let me know in the chat box if you got the concept of percentage yield properly or not, so that I can talk about percentage purity right here in detail. Let me know in the chat box first. If every single thing is damn clear to you or not. Let me know in the chat box. Let me know in the chat box. Yes, Sweet English will do one short series of atomic structure as well. Just wait for it. Yeah. Rashika, this is the English channel. I'm not supposed to talk in Hindi. Varna Hindi मेरे को अच्छे से आती है. This is the complete English channel, yeah. This is for the ones actually who cannot understand Hindi. Okay, let's move on and let's talk about something called as percentage purity, okay? I'll just give you the brief idea of percentage purity, then we are going to solve the problems on the basis of this concept, percentage purity, right here, okay? Understand, guys. In order to calculate the percentage purity of the substance, it is defined as mass of pure compound divided by mass of impure sample multiplied by 100. This is the simplest formula by means of which we can calculate the percentage purity of any substance, yeah? Now guys, how do we get to know this concept of percentage purity right here, okay? Let's say I've got a container and in this container I have got calcium carbonate, and with this calcium carbonate I have got few impurities as well. With this calcium carbonate right here. So people, this sample which I have right here, shouldn't I be calling this as impure sample of calcium carbonate? Yes, I'm calling this as impure sample of calcium carbonate. Absolutely, impure sample of calcium carbonate. Let's assume the mass of impure sample of calcium carbonate right here is 50 grams. Yes, let's assume mass of impure sample of calcium carbonate right here is 50 grams. Yes. Now guys, let's assume out of these 50 grams of the total sample, let's say 30 grams of calcium carbonate is present in the pure form. Let's say in this container you have got the pure 30 grams of calcium carbonate. So I can say this is the mass of pure calcium carbonate. Absolutely, this is the mass of pure calcium carbonate. So people, in order to calculate the percentage purity of calcium carbonate, I'll be simply writing mass of pure calcium carbonate, which is 30 grams, divided by mass of impure sample, which is 50 grams, multiplied by 100. Whatever value you are getting right here, that is going to be the value of percentage purity right here. Yes, very, very simple. Yes, right? Yes, Siddhi, this is for NEET students as well. Yes, NEET students can also watch these. Yes, absolutely. Why not? Correct? So people, so with this, by means of this technique, we get to know the percentage purity of any compound in the impure sample. Correct? Very, very, very simple. Right? Understand, guys, what I'll say. I'm going to take one more container right here so that you master this concept properly. Then I can directly move to the questions. Yes. Let's say I've got NaCl right here, and with this NaCl, you have got few impurities as well. You have got some impurities as well with this NaCl right here. Okay. So people, should I be calling this sample as the pure sample of NaCl or impure sample of NaCl? I'll be definitely calling this as the impure sample of NaCl. Yeah. I'll be calling this as the impure sample of NaCl. Let's assume mass of impure sample of NaCl right here is, for example, 80 grams. And let's assume out of 80 grams of the sample, let's say 30 grams is the mass of pure NaCl in the sample. Let's assume 30 grams is the mass of pure NaCl in the sample. Now people, if I simply want to calculate the percentage purity right here, can I say percentage purity of NaCl? Percentage purity of NaCl is going to be mass of pure NaCl, which is 30, divided by mass of impure sample, which is 80, multiplied by 100. Whatever value you'll be getting right here, that is going to give you the value of percentage purity of NaCl right here. Very, very, very simple. Yeah. Now guys, there is something important which you need to understand right here. I'm going to write few important statements which you actually need to decode right here. Okay, I'm going to write few important points which you actually need to decode right here. And what are those important points? I'm writing a statement over here. I'm writing something called as 50 grams of 80% pure, 50 grams of 80% pure NaCl. Yes. What does this statement mean? What all things can we depict from this statement? Understand properly what I'll say. Okay. See guys, Akansha, I'm not supposed to talk in Hindi. There are a lot of Hindi channels of Vedantu as well. This is complete English channel. I'm not supposed to speak a single word in Hindi as well. Yeah. So if you want to attend the Hindi lectures, there is Arvind Arora sir taking in Hindi. Yes, there is the JEE channel also, Vedantu JEE, that is also in Hindi. Yes, where Abhinav sir takes, Harsh sir takes. You can join that. Okay, I hope you get it. Okay, now guys, I wrote one statement right here: 50 grams of 80% pure NaCl. Correct? 50 grams of 80% pure NaCl. What all things can I get from here? What all things can I get from here? Understand. I can say, guys, the sample which I'm given with right here, that is basically the impure sample of NaCl. And I'm given with the mass of impure sample of NaCl. The mass of impure sample of NaCl is given to me as 50 grams. Now guys, understand the statement: 50 grams of 80% pure NaCl. That means among these 50 grams, 80% of this 50 grams is present in the form of pure NaCl. I can simply say 80 grams of this 50 grams is present in the form of pure NaCl. So I can say mass of pure NaCl right here is simply equal to 80% of the total sample, 80% of the 50 grams. Isn't it going to be 80 divided by 100 multiplied by 50? Can I say this value will come simply as 40 grams? So I can say out of total 50 grams of impure sample, we have got 40 grams. We have got 40 grams of NaCl in pure form as well, right? Similarly, guys, I'm going to write one more statement by means of which all these things will get clear to you so that I can move on directly to the concepts. Yes? Yes? Understand, guys. Understand properly what I'll say. See, I'm writing something like this. I'm writing 40 grams of 30%. 40 grams of 30% pure calcium carbonate. 40 grams of 30% pure calcium carbonate. What all things can we get from here? Right? Understand, guys. See, This 40 grams, this is the mass of impure sample of calcium carbonate, right? I can say 40 grams is the mass of impure sample of calcium carbonate. Yes. Now, out of these 40 grams, 30% of this 40 grams is present in the form of pure calcium carbonate. So I can calculate the mass of pure calcium carbonate right here. So I'll say the mass of pure calcium carbonate is simply going to be 30% of 40 grams. Yes, it's going to be 30% of 40 grams. Yes. So once you get the value, you are going to get it as 12 grams. So people, I can say 12 grams will be the pure mass of calcium carbonate right here in this sample. Yeah. Very, very, very simple, correct? Now guys, remember a few important things. In a chemical reaction, I'm writing one important statement right here, then only I can move the questions, okay? I'm writing something like this. In a chemical reaction, I mean, only a pure substance participates. Only a pure substance participates. Yes, in a chemical reaction, only a pure substance participates. Impurities never participate in the reaction. Yes, impurities never participate in the reaction. It is only the pure substance which participates in a chemical reaction. Impurities are never going to participate in a chemical reaction. Yeah. Now guys, see guys, how I'll be using all these concepts in the form of questions, right? The first basic question which I have right here, understand this. 50 grams of 80% pure calcium carbonate is heated. Calculate the volume of carbon dioxide gas produced at STP. So people, I'm given with calcium carbonate and I'm heating this calcium carbonate up, and as you all must be knowing, it gets converted to calcium oxide solid plus carbon dioxide gas, which is getting liberated right here. Now people, regarding this calcium carbonate, I'm given with one statement, right? Which I just now, few minutes back, I told you how to decode this sort of a statement. Yes, few minutes back I told you. What is given to me, guys? There is something given to me as 50 grams of 80% pure. 50 grams of 80% pure calcium carbonate. Yes, what all things can we depict from here, right? People, if I ask you, are these 50 grams the pure mass of calcium carbonate? No way. This 50 grams is going to be the mass of impure sample. So first of all, I need to check out of these 50 grams, what is the pure mass of calcium carbonate? And that pure mass of calcium carbonate is going to participate in this reaction right here, okay? So I can say 80% of 50 grams. Yes, I can say 80% of 50 grams, 80% of 50 grams is present in the form of pure what? Is present in the form of pure calcium carbonate, right? So I'll say 80 divided by 100 multiplied by 50 will come out to be 40 grams. So 40 grams is the mass of pure calcium carbonate. And people, in the reaction, only pure mass of calcium carbonate will participate. Impurities are not going to participate right here. Yes? Yes? Now guys, understand. I got to know the pure mass of calcium carbonate. Yes. So this pure mass of calcium carbonate is going to participate in this reaction. Yes. This pure mass of calcium carbonate is going to participate in this reaction. Yes. Understand guys what I'll say. If this is the pure mass of calcium carbonate, can I say the pure moles of calcium carbonate are going to be, given, pure mass of calcium carbonate divided by molar mass of calcium carbonate, it's going to be 0.4 moles. So 0.4 moles we have the pure calcium carbonate with us. Yes. Nandini, just take the video a little back. It'll be automatically a replay for you. Yeah. So what I'm saying right here, the pure moles of calcium carbonate we have with us, that is 0.4. Yes. Now guys, I can use the stoichiometry. Yeah. I can use the stoichiometry. Understand properly what I'll say. See guys, it's a balanced chemical equation. The stoichiometry coefficient right here is 1. The stoichiometry coefficient right here is 1. Can I simply say something like this? Can I say 1 mole of calcium carbonate? 1 mole of calcium carbonate gives 1 mole of carbon dioxide. Yes. Can I say 1 mole of calcium carbonate gives 1 mole of carbon dioxide? People, do we have 1 mole of calcium carbonate or we have 0.4 moles of calcium carbonate? In this reaction, 0.4 moles of calcium carbonate are going to be participating. Yes, so 0.4 moles of calcium carbonate should give 0.4 moles of carbon dioxide. So people, these are the moles of carbon dioxide getting liberated right here. But was I supposed to calculate moles of carbon dioxide liberated or volume of carbon dioxide liberated? I was supposed to calculate volume of carbon dioxide liberated, and we know at STP volume of carbon dioxide liberated will be equal to moles of carbon dioxide liberated multiplied by 22.4 liters. So it's going to be simply 0.4 multiplied by 22.4. The value is going to come as 8.96 liters. So I'll say 8.96 liters of carbon dioxide will be getting released, will be getting evolved right from this reaction right here. Yes? Let me know in the chat box if everything is clear to everyone or not. Let me know in the chat box, guys, if everything is damn clear to everyone so that I can move on and talk about few more interesting things right here. Let me know in the chat box fast, yeah? Yes? Look, I'll be taking chemical bonding soon. Just wait for it, yeah? I'll be taking chemical bonding soon. Yes? Okay, let's move on, guys. Let's try to do a few more questions by means of which all your concepts will get cleared, yeah? Understand? Understand, guys. I told you, first of all, in a chemical reaction, only the pure substance participates. Yes? In a chemical reaction, only the pure substance participates. Impurities are never going to participate in a chemical reaction. We know that, yeah? See, 5 grams of H2SO4, right? I'm given with 5 grams of H2SO4. Or let me write the reaction over here again. It's going to be H2SO4 and it's reacting with 2 times NaOH. It's reacting with 2 times NaOH and it leads to the formation of Na2SO4 right here. And with this Na2SO4, you get water at the same time. Yes. This is something which you get. This is something which you are getting right here. Yes, absolutely. Now, guys, see, understand properly, okay? 5 grams of H2SO4. 5 grams of H2SO4 sample. Understand the language of the question. 5 grams of H2SO4 sample. So, is this, so I'm writing over here sample, guys. It's mentioned sample. So, is it the pure mass of H2SO4, or I can say this is the impure mass of sample. This is the impure mass of sample of H2SO4. So people, this 5 grams is the impure mass of, this is the impure mass of sample. Yes, this is the impure mass of sample. What am I supposed to calculate? I'm supposed to calculate percentage purity of H2SO4 in the sample. How should I be approaching to this sort of equation? Yes, understand what I'll be doing? Very, very simple thing. See, guys, what about the molar mass of H2SO4? Can I say it's 98 grams? Yes. 98 grams is the mass of 1 mole of H2SO4. Yes. And over here, I've got 1 mole only. Correct. What about the molar mass of NaOH? It's going to be 40 grams. 40 grams is the mass of 1 mole of NaOH, but I have 2 moles. So 40 multiplied by 2 is 80 grams. Yes. So people, can I say something like this? Understand properly. Can I say 80 grams of NaOH? 80 grams, as per stoichiometry, 80 grams of NaOH reacts with 98 grams of H2SO4. Yes. As per stoichiometry, I got to know 80 grams of NaOH should react with 98 grams of H2SO4. So can I say 1 gram of NaOH should react with 98 divided by 80 grams of H2SO4? Yes. But people, do I have only 1 gram of NaOH, or we have 4 grams of NaOH? We have 4 grams of NaOH. Can I say 4 grams of NaOH should react with 98 divided by 80 multiplied by 4? The value is going to come as 4.9 grams of H2SO4. So as per stoichiometry, I got to know with 4 grams of NaOH, 4.9 grams of H2SO4 are going to react. Yes, and that mass of the reaction, that mass of the substance which participates in the reaction, can I say that is going to be the pure mass of the substance? So people, I can say this is the pure mass of H2SO4. This is the pure mass of H2SO4, because from the stoichiometry, I got to know this much amount of H2SO4 is participating in the reaction, and that amount of reactant, or that amount of reactant which participates in a chemical reaction, that will be the pure mass. That will be the pure mass of this H2SO4 right here. Yes. So people, I got the pure mass of H2SO4. I have the impure mass of sample. Yes, I have both the ones. I can simply calculate the percentage purity. Yes, I can say percentage purity of H2SO4. It's going to be equal pure mass of H2SO4, which is how much? Pure mass of H2SO4 is 4.9. Impure mass of the sample, that is 5, multiplied by 100. You'll get the values exactly equal to 98%. So I can say percentage purity of H2SO4 in this sample right here is 98. Yes. Let me know in the chat box if everything is clear till here, so that I can move on and talk about few more interesting things right here. Yeah. Let me know in the chat box fast, guys. Let me know in the chat box fast. Okay, let's move on, guys. Let's move on. Let's move on. There is one more question which we have on our screen. Have a look, guys. You can easily kill this question now, yeah? You can easily solve this question now. Understand? As per the question, calculate the amount of calcium oxide in kilograms, okay? Or let's not calculate in kilograms, let's calculate in grams only, okay? Calculate the amount of calcium oxide in grams that can be produced on heating 200 grams of limestone. 200 grams of limestone, that is 90% pure calcium carbonate. Yes. So people, I'm given with 200 grams of limestone. I'm given with something called as 200 grams of limestone. This is something which is given to me, and it's mentioned clearly in the question, out of 200 grams of limestone, 90% of limestone is present in the form of pure calcium carbonate. I'll say 90% of this total amount, 90% of this 200 grams is present in the form of pure calcium carbonate, right? So I can get the mass of pure calcium carbonate from here. It is simply going to be 90 divided by 100 multiplied by 200. It's going to be 180 grams. So people, I can say out of 200 grams of limestone, there will be 180 grams of calcium carbonate actually, and only 180 grams of calcium carbonate are going to participate in this reaction. Yes. Yes. Understand, guys, what I'll be doing? Understand what I'll be doing? See. Can I say simply like this? The molar mass of calcium carbonate is 100 grams. Can I say 100 grams is the mass of 1 mole of calcium carbonate? Yes. It is the mass of 1 mole of calcium carbonate. Yes. What is the molar mass of carbon dioxide? Do I have to calculate carbon dioxide or calcium oxide? I need to calculate calcium oxide. What is the molar mass of calcium oxide? You will say 56 grams. So 56 grams is the mass of 1 mole of calcium oxide. Yes. So people, can I say right here, as per the stoichiometry of the reaction, can I say 100 grams of calcium carbonate? 100 grams of calcium carbonate should give me 56 grams of calcium oxide. Yes. So can I say something like this? 1 gram of calcium carbonate should give me 56 divided by 100 grams of calcium oxide. Yes. Now people, in this reaction, are 200 grams of calcium carbonate participating or 180 grams of calcium carbonate? Since in this 200 grams of limestone, we got to know only 180 grams are present in the form of pure calcium carbonate. So 180 grams of calcium carbonate are going to participate in this reaction. So 1 gram gives 56 divided by 100 grams of calcium oxide. So I can say 180 grams of calcium carbonate should give me 56 divided by 100 multiplied by 180 grams of calcium oxide. So people, you'll be getting this much amount of calcium oxide right here. Okay. Let me know in the chat box if everything is clear to you or not. Let me know in the chat box, guys. Let me know in the chat box if it's clear to you or not. Let me know fast. Let me know fast. Yes. Yeah. Is it clear to everyone? Let me know fast. Yeah. Jahangir, you can take the video back. It will be automatically a replay. Okay. Just take the video a little back. It will be automatically a replay. Just use this little bit of common sense. Yeah. Okay. Virat, it's simply 90% of 200 grams. That means 90 divided by 100 multiplied by 200. That comes out to be 180, yeah? Yes. So people are saying it's coming as 100.8 grams. So I got to know 100.8 grams of calcium oxide is actually getting formed right here through this reaction, okay? Right? Okay. Let's move on, guys. Let's move on and let's talk about few more questions right here. Let's talk about few more questions right here. This is the question on your screen. You can easily solve this one as well now. You can easily solve this one as well now. See guys, how will I be approaching this sort of a question? 400 grams of limestone, which is the impure calcium carbonate, yeah? 400 grams of limestone is treated with oxalic acid to yield 512 grams of calcium oxalate. Calculate the percentage purity of calcium carbonate in limestone sample, okay? So people, I've got 410 grams of limestone, yes, which is the impure calcium carbonate, okay? Now people, if I'll start with 410 grams of limestone and if I'll make this 410 grams of limestone to react with oxalic acid, it leads to the formation of 512 grams of calcium oxalate, okay? I need to calculate percentage purity of calcium carbonate in this sample, okay? How will I be solving this sort of equation? How will I be solving this sort of equation? Understand? See guys, see. First of all, As you all must be knowing, what is the molar mass of calcium carbonate? It's 100 grams. Yes, 100 grams is the mass of 1 mole of calcium carbonate. What is the molar mass of calcium oxalate, guys? Let's calculate it. Calcium is simply 40, carbon 2 is 24, yes, oxygen is 64. So it's going to be 4, 4, 8, 4 to 6, 6, 6, 12, 128. So 128 grams is the molar mass of this calcium oxalate right here. So 128 grams is the mass of 1 mole of calcium oxalate right here. So can I say 100 grams of calcium carbonate gives 128 grams of calcium oxalate right here? I can say that. Or people, I can just take the reverse of this statement as well. I can say 128 grams of calcium oxalate. 128 grams of calcium oxalate are produced from 100 grams of calcium carbonate. 100 grams of calcium carbonate. Yes. So people, can I say something like this? 1 gram of calcium oxalate must be produced from 100 divided by 128 grams of calcium carbonate. Yes. So people, is 1 gram of calcium oxalate getting formed through the reaction, or 512 grams of calcium oxalate is getting formed? 512 grams of calcium oxalate is getting formed. So I can say 512 grams of calcium oxalate must be produced from 100 divided by 128 multiplied by 512. The value is going to come as 400 grams of calcium carbonate. Yes. So people, I can simply say 512 grams of calcium oxalate will be produced from 400 grams of calcium carbonate. Yes. So can I say, guys, can I say this 410, this is the mass of limestone, this is the mass of impure calcium carbonate, and I got to know 512 grams of calcium oxalate should be only produced from 400 grams of calcium carbonate. Yes, as per stoichiometry. And that mass of the substance which participates in the reaction, that is going to be the pure mass. Can I say only 400 grams of calcium carbonate will be participating in the reaction? I got the pure mass of calcium carbonate. I know the impure mass of the sample. I can easily calculate percentage purity of calcium carbonate. Isn't it simply going to be mass of pure calcium carbonate, which is 400, which I got to know through the stoichiometry? Yes, divided by mass of impure sample, which is 410, multiplied by 100, you'll be getting the percentage purity of calcium carbonate right here. Yes, it is absolutely going to come as 97%. So people, 97% of this 410 grams of limestone is present in the form of pure calcium carbonate right here. Yes, correct. Yes. Okay, let's move on, guys. Let's move on. This is one very, very nice question right here, guys. This is a nice question right here. Okay, very, very nice question. Understand what I'll be doing. 10 ml of H2O2. Okay, there is something missing. Aqueous solution. Okay, 10 ml of H2O2 aqueous solution reacts with Ki to produce 0.5 grams of iodine. 0.5 grams of iodine. Calculate the percentage purity of H2O2. I'm supposed to calculate percentage purity of H2O2, correct? So can I say percentage purity of H2O2 is going to be mass of pure H2O2? Mass of pure H2O2 divided by mass of impure sample. Mass of impure sample multiplied by 100. This is the formula I'll be using in order to calculate the percentage purity right here. Yes. Now see, guys, how will I be solving this sort of equation, right? Let me tell you, the density of H2O2 aqueous solution is equal to 1 gram per ml. The density of H2O2 aqueous solution is equal to 1 gram per ml. Yes. So people, can I say something like this? Can I say 10 ml of H2O2 solution? I have got 10 ml of H2O2 solution whose density is 1 gram per ml. Can I say density of H2O2 sample right here, density of H2O2 solution right here, it is equal to 1 gram per ml. Density of the solution will be mass of solution, mass of H2O2 solution divided by volume of H2O2 solution. It is going to be 1. So can I say mass of H2O2 solution right here is simply going to be 10 grams? Yes, because volume of solution multiplied by 1. Yeah. So people, one thing which I got to know right here. What is that? I got to know this 10 ml of H2O2 solution, it means 10 grams of H2O2 solution. I got to know that the mass of this 10 ml of H2O2 aqueous solution is going to be 10 grams of H2O2 solution, correct? Now it reacts with Ki to produce 0.5 grams of iodine, right? this H2O2, it reacts with Ki to produce 0.5 grams of iodine right here, okay? Now people see what I'll be doing. Understand what I'll be doing, okay? What is the molar mass of H2O2? Can I say 34 grams? Can I say 34 grams is the mass of 1 mole of H2O2? Absolutely. What is the molar mass of I2? You should be knowing it is 254 grams. Can I say 254 grams is the mass of 1 mole of I2? Yes. Can I say something like this, guys? 254 grams. 254 grams of I2 are produced from 34 grams of H2O2. Yes. So I can say 1 gram of H2O2 should be produced from 34 divided by 254 grams of H2O2. Yes. So is 1 gram of iodine getting formed or 0.5 grams of iodine getting formed? I can say 0.5 grams of iodine should get formed from 34 divided by 254 multiplied by 0.5 grams of H2O2, right? So I can say as per the reaction, 0.5 grams of iodine should get produced from this much amount of H2O2, right? So this is the actual mass of H2O2 which is participating in the reaction. Yes, and that mass of H2O2 which participates in the reaction, it's going to be pure mass of H2O2. So people, I got the pure mass of H2O2. I know the impure mass of the sample of H2O2. I know both the things. I can simply get what? I can simply get the percentage purity right here. I can say percentage purity is equal to mass of pure H2O2, which is this much, yes, divided by mass of impure H2O2, which is this much, multiplied by 100. You'll be getting the final answer, I guess, as 0.06 something, yeah, 0.063%, yeah. This is going to be the percentage purity of the sample, which you'll be getting at the end, right? Yes. Okay. Got it? Yes, should I move ahead, guys? Should I move ahead? Should I move ahead? Let me know in the chat box. Should I move ahead? Yeah? Okay. Understand. Or if you can go to some other channel, bro, if that is a scene. You can go to some other channel. If you have come up here, I mean, to divert the attention of the students, you can go to some other channel, do that over there also, okay? Right? Let them study. Okay. Now, people, there is something called as mixture analysis. There is something called as mixture analysis, right? There is something called as mixture analysis. How do we get to know this concept of mixture analysis? I'm going to make you understand this concept of mixture analysis in the form of question, okay? In the form of question, I'm going to make you understand, okay? Understand what I'll be saying. For example, guys, I'm writing one question right here for you so that you get to know the concept of mixture analysis properly right here, okay? Understand what I'll be saying. See, guys, I'm writing something like this: 1 gram of a mixture of 1 gram of a mixture of aluminum and zinc, or let's keep it as aluminum and magnesium. 1 gram of a mixture of aluminum and magnesium reacts with HCl to produce 1.12 liters of H2 gas at STP. Calculate the mass of each component in the mixture. Calculate the mass of each component in the mixture. Yes, calculate the mass of each component in the mixture. This is the question which is given to me, okay? Now the point is how to approach to this sort of a question. Right? Yes, top face, I know Paul sir, yes, absolutely, why not? I know him, yes, we are colleagues only. Okay, see guys, see what is given to me and what are we supposed to calculate, okay? Understand properly what I'll say. See, first of all, I'm given with one mixture, right? It contains what? It contains aluminum and magnesium. The mass of the mixture is given to me as 1 gram, yeah. The mass of the mixture is given to me as 1 gram. Right? Now, people, it's mentioned in the question, we are making this mixture to react with HCl. And when this mixture reacts with HCl, what happens? H2 gas is getting liberated. And how much H2 gas is getting liberated? Volume of H2 gas which gets liberated right here, that is 1.12 liters. Yes? And everything is happening at STP. And everything is happening at STP. Yes? Now, people, since you know how much volume of H2 gas is getting liberated, so you can easily tell me how many moles of H2 gas will be getting liberated. It's going to be volume of H2 gas getting liberated divided by 22.4. Yes. Can I say these will be the moles of total moles of H2 getting liberated from here? Yes. Yes. Very, very simple concept this is, guys. These will be the moles of the H2 gas which will be getting liberated right here when this mixture will be reacting with HCl over here. Yes? Now we will see. See what I'll be doing. See what I'll be doing. Understand. See, we have got 1 gram of the mixture. Right? This 1 gram is the mass of the mixture. This is the mass of aluminium as well as magnesium. Let's assume out of 1 gram, x grams is the mass of aluminium in the mixture. So it's going to be 1 minus x. 1 minus x grams is going to be the mass of magnesium in the mixture. Now, people, if I divide this x by the molar mass of aluminium, which is 27, can I say this x by 27 will give me the moles of aluminium in the mixture? Can I say 1 minus x divided by molar mass of magnesium? Can I say this term is going to give me the moles of magnesium in the mixture? Yes. Now, people, what is the concept which I'll be using right here in this question? Let me tell you, when this mixture is allowed to react with HCl, some amount of HCl will react with aluminium, some amount of magnesium, some amount of HCl will react with magnesium right here. So what is going to happen? Let's get to know that in the form of reactions. I'll say when some amount of aluminum is going to react with HCl, it will lead to the formation of AlCl3, and with AlCl3 you'll be getting H2 gas as well. So H2 gas will be getting liberated through this reaction. At the same time, when some amount of HCl will react with magnesium, what is going to happen? I'll write magnesium plus HCl. Magnesium plus HCl. It will lead to the formation of MgCl2, and from here you'll be getting again the H2 gas liberated. Yeah. Now, people, what is happening basically when HCl is allowed to react with aluminium and magnesium, H2 gas is getting liberated. How much H2 gas is getting liberated? 1.12 liters. These many moles of H2 gas are getting liberated right here. Yes, these many moles of H2 gas are getting liberated right here. And I got to know something like this. That some amount of HCl will be reacting with aluminum and will be liberating H2 gas, and some amount of HCl will be reacting with magnesium and will be liberating H2 gas. Yeah. Yes. Now, guys, see what I'll be doing. What I'll be doing right here, I'll be using the stoichiometry of the reaction, and by using the stoichiometry of the reaction, I'll get to know how many moles of H2 will get liberated from this reaction and how many moles of H2 will be getting liberated from this reaction. Yes. So I can simply use the concept number of moles of H2 getting liberated from first reaction plus number of moles of H2 getting liberated from second reaction should be equal to total moles of H2 getting liberated. Yes, that is the concept which I'll be using. Correct? Now, people, in order to use this concept, I should balance the reaction first. Yes, let's try to balance the reaction. This should be 3 times. This should be 3 divided by 2 times. The reaction is balanced. Yes. Now, people, let's try to balance the second reaction as well. This should be 2 times and this should be 2 times. Correct? Now, people, from the stoichiometry of the reaction, can I say 1 mole of aluminum gives 3 by 2 moles of H2, right? But do I have only 1 mole of aluminum in the mixture, or I have x by 27 moles? Yes, 1 mole gives 3 by 2 moles. So I will say x by 27 moles of aluminum will give me 3 divided by 2 multiplied by x divided by 27 moles of H2. Yes, so I can say these many moles of H2 are getting liberated from reaction number 1. Similarly, can I calculate the moles of H2 getting liberated from reaction number 2 as well? I can do that. Yes, we got to know 1 mole of magnesium gives 2 moles of hydrogen. But do I have 1 mole of magnesium or 1 minus x by 24 moles? I have 1 minus x by 24 moles of magnesium. Can I say something like this? 1 minus x divided by 24 moles of magnesium will be liberating something like this. Just a second. Is the reaction balanced? I think this reaction is not balanced. Is that? No, it's not balanced. Let's remove this 2 over here. Yeah. Just a second, guys. Let's remove this 2 over here. Yeah. Now the reaction is balanced. This 1 Mg, this Cl2, this H2. Yeah. Now, guys, see. Understand. See, I can say 1 mole of magnesium gives 1 mole of H2. So 1 minus X divided by 24 moles of magnesium should give me simply 1 minus X divided by 24 moles of H2. So I can say I got the moles of H2 which are getting liberated from reaction number 2 as well. These are the moles of H2 getting liberated from reaction number 2. So how many total moles of H2 are getting liberated? These many. So can I say number of moles of H2 getting liberated from reaction number 1 plus number of moles of H2 getting liberated from reaction number 2 should be equal to total moles of H2 getting liberated, right? Yes. So what I'll be doing? The question is dusted, guys. The question is done and dusted. I'm going to use one simple concept right here. I'll say number of moles of H2 getting liberated from reaction number 1 plus number of moles of H2 getting liberated from reaction number 2. That should be equal to total moles of H2 getting liberated. Yes. So people, I'll be getting one simple equation right here. Number of moles of H2 getting liberated from reaction number 1, it's simply going to be 3 divided by 2 multiplied by X divided by 27, correct? Plus number of moles of H2 getting liberated from reaction number 2 is going to be 1 minus X divided by 24, yes, is equal to total moles of H2 which are getting liberated, that is 1.12 divided by 22.4 over here. People, when you will solve this equation, are you guys going to get the value of X? Absolutely, because in this equation I've got only one variable, and if you'll solve this equation you'll get the value of X as 0.6. and what was X? X was the mass of aluminum in the mixture. So mass of aluminum in the mixture is 0.6 grams. So mass of magnesium in the mixture is going to be 1 minus X. 1 minus 0.6 means 0.4 grams. So I got to know what will be the mass of each component right here in the mixture. Yes, let me know in the chat box if it is clear to every single guy right here or not, so that I can move on and talk about a few more interesting things. Let me know in the chat box, guys. Let me know in the chat box fast. Yes? Yes? Okay, let's move on then. Yes, okay. Let's move on. Let's try to do one more question by means of which all this mixture analysis will get clear to you, okay? Let's try to do one more question. With that, things will get clear to you, yeah? I'm going to write one more question right here for you so that you get to know it properly. I'm going to write something like this. 1.67 grams of a mixture of 1.67 grams of a mixture of aluminium and zinc reacts with, I'm using the term reacts with, yes, reacts with excess of HCl to produce what? To produce 1.69 liters of H2 gas at STP. Calculate the mass of aluminium and zinc in the mixture. Calculate the mass of aluminium and zinc in the mixture. Yes? Yes? Right? Now guys, see. What I'll be doing right here is, see, understand properly what I'll say. See guys, I'm given with a mixture right here. Let's say I've got a mixture, and in this mixture, what do I have? I've got aluminium and zinc right here. I've got aluminium and zinc right here in the mixture. What is the mass of mixture which is given to me? The mass of the mixture which is given to me is 1.67 grams. Yes, this is the mass of the mixture which is given to me. Now people, it's mentioned that the mixture is reacting with HCl. The mixture is reacting with HCl. And when this mixture will react with HCl, I can say some amount of HCl will react with aluminium, some amount of HCl will react with zinc. Okay? And what will happen eventually? H2 gas will be getting liberated. And how much volume of H2 gas will be getting liberated? 1.69 liters. So I can say volume of H2 gas which gets liberated right here is 1.69 liters. Yes, this is the volume of H2 gas which is getting liberated right here. Correct? Now people, can I simply say like this? Can I say number of moles of H2 which will be getting liberated right here will be 1.69 divided by 22.4. Can I say these many moles of H2 are getting liberated over here? Yeah, absolutely correct. Now guys, what I'll be doing right here, understand what I'll do. See, I've got 1.67 grams of mixture. Yes, let's assume out of 1.67 grams there is X grams of aluminum in the mixture. So zinc is going to be what? Zinc is going to be 1.67 minus X. So this is going to be, this X, this is the mass of aluminum in the mixture. This 1.67 minus X, this is going to be the mass of zinc in the mixture. Yeah. Now people, if I divide this X by the molar mass of aluminum, which is 27, I will be getting the number of moles of aluminum in the mixture. If I divide this term 1.67 minus X by the molar mass of zinc, it's going to be 65. I'll say this term is going to give me the moles of zinc in the mixture. Yeah. Now guys, can I say something like this? Can I say some amount of HCl will react with aluminium and some amount of HCl will react with zinc? Yes. And we know when aluminium reacts with HCl, it leads to the formation of AlCl3, and with this AlCl3 you get H2 gas at the same time. Yes. And people, when some other amount of HCl will react with zinc, what is going to happen? Zinc will react with HCl and it will lead to the formation of ZnCl2, and with this ZnCl2 you'll be getting the H2 gas at the same time. Yes. What is the total moles of H2 gas getting liberated? These are the total moles of H2 gas getting liberated. Yes. Yes. Now people, can I say out of total moles of H2 getting liberated, some moles of H2 will be getting liberated from reaction number 1 and some moles of H2 will be getting liberated from reaction number 2. Correct? Now people, what I'll be doing right here is I'll be balancing the reaction first. Yeah. I'll be balancing the reaction first. Correct? Now guys, let's try to balance the reaction. Right? And we know how to balance it. This should be 3 times. This should be 3 divided by 2 times. Yeah, the reaction is balanced. Absolutely. Now guys, is this reaction balanced? This reaction is not balanced, so this should be only 2 times. Correct? Now guys, say, understand what I'll be doing. I'll be simply using the same procedure which I did in the last question. Yeah? Yes? See guys, we know 1 mole of aluminium gives 3 by 2 moles of H2. Do I have 1 mole of aluminium or I have X by 27 moles of aluminium? I have X by 27 moles of aluminium. Yes, I can say 1 mole of aluminium gives 3 by 2 moles of H2. So X divided by 27 moles of aluminium should give me 3 divided by 2 multiplied by X divided by 27 moles of H2 right here. So these are the moles of H2 which are getting liberated from reaction number 1. These are the moles of H2 which are getting liberated from reaction number 1. Yes. Now similarly guys, can I say 1 mole of zinc gives 1 mole of H2? So how many moles of zinc do we have? We have 1.67 minus X. 1.67 minus X divided by 65 moles of zinc. If 1 mole of zinc gives 1 mole of H2, so these many moles of zinc should give me 1.67 minus X divided by 65 moles of H2. So these will be the moles of H2 getting liberated from reaction number 2. Yeah. Now people, which concept I'll be using? I can say only one concept. I can use a single concept right here. What is going to be that? That is going to be number of moles of H2 getting liberated from reaction number 1 plus number of moles of H2 getting liberated from reaction number 2 should be equal total moles of H2 getting liberated. Yeah. That is the concept which I'll use. Correct? I'll say something like this. Number of moles of H2 getting liberated from reaction number 1 plus number of moles of H2 getting liberated from reaction number 2 is equal to total moles of H2 which get liberated. Yes? Correct? Now guys, what I'll be doing? Number of moles of H2 which gets liberated from reaction number 1. How much that was? That was simply what? That was 3 divided by 2 multiplied by X by 27. Yes? Do you remember that? Correct? I'll be writing something like this. 3 divided by 2 multiplied by X divided by 27. These were the moles of hydrogen getting liberated from reaction number 1 plus moles of hydrogen getting liberated from reaction number 2. It's going to be 1.67 minus X divided by 65, right? This should be equal to the total moles of H2 which are getting liberated. It's going to be 1.69 divided by 22.4 right here. People, can I say I got one equation, and in this one equation I've got only one variable X, and once I've got one equation, one variable, I can get the value of X right here. And whatever is going to be the value of X, that will be the mass of aluminum in the mixture. And once you get the X value, you'll be getting 1.67 minus X at the same time. So this is going to be the mass of zinc over here. And people, as far as I remember, the value of X, you'll be getting something as 0.42 grams. Yes, so what is X? X was the mass of aluminum in the mixture. Yes, so people, I can say mass of zinc you'll be getting as 1.67 minus 0.42. It's going to be simply equal to 1.25. So there'll be 1.25 grams of zinc present in the same mixture right here. Yes, let me know in the chat box if it is clear to every single guy. Let me know in the chat box if it is clear to every single guy right here, so that I can move on and talk about a few more interesting things. Yeah, let me know in the chat box guys first. Let me know in the chat box. I want every one of you to say it. Okay. Ji, Ubi, I'll be considering it. Yes. My throat is already paining. Yeah, you know that. Okay. Let's move on, guys. Let's move on. And let's enter into one more thing, which is what we call as concentration terms. Yes. What are concentration terms all about? What are concentration terms all about? Okay. Before talking about the concentration terms, guys, I need to give you the brief introduction of few basic things which you must remember first of all, okay? Understand what I'll be doing. See, let's say, guys, I have got a solution. Let's say I've got the solution, and as you all must be knowing, the solution, it consists of two terminologies. It consists of two things. One is called as solute. Another one is called as solvent, right? Remember, solvent from now onwards I'll be representing by the number 1 and solute I'll be representing by number 2. Okay. Now people, if I write something like this, if I write W2, W2 will stand for mass of solute. It will stand for mass of solute. If I write something as W1 stands for mass of solvent. If I write something as M2 will stand for molar mass of solute, yes, and M1 will stand for molar mass of solvent, yes. Similarly, guys, if I write something like N2 will be number of moles of solute, yes, and if I'll be writing N1 will be number of moles of solvent right here, okay. Very, very simple thing, correct? And as you all must be knowing, guys, mass of solution for a binary solution I'm talking about, mass of solution is always equal to mass of solvent plus mass of solute. Remember this at the same time for a particular solution, yeah? Now, guys, there are certain terminologies which you must remember right now, which you must know right now, okay? What are those terminologies? What are those concentration terms? I'll be exactly starting from the first concentration term, which is what we call as weight by weight percent of the solute, or we call this as mass percent of the solute, right? Weight by weight percent of the solute, or we call it as the mass percent of the solute. Understand what I'll say. See, guys, weight by weight percent of the solute, it is simply defined as mass of solute present in 100 grams of solution. It is simply defined as mass of solute present in 100 grams of solution. And how do we, what is its formula? Its formula is simply mass of solute in grams divided by mass of solution in grams multiplied by 100. This is the simplest way by means of which we can define the mass percent of solute. Yes. Now, guys, see, I'll be writing one statement over here, and you need to decode that statement, correct? What statement I'm going to write? I'm going to write something like this: 20%. I'm going to write something like this: 20% weight by weight of NaCl aqueous solution. Okay. What does it mean over here? 20% weight by weight of NaCl aqueous solution. What does it mean? It simply means, guys, 20 grams. 20 grams of NaCl is present in 100 grams of solution. 20 grams of NaCl is present in 100 grams of solution. So can I simply say I got the mass of solute right here? Yes, which I will be representing by W2. Can I say this is the mass of solution right here? Absolutely. People, I got the mass of solute. I got the mass of solution. Can I get the mass of solvent? 100 minus 20, which is going to be 80 grams. So 80 grams is going to be the mass of solvent right here. Yes, very, very simple. Correct? Correct? Very simple, absolutely. Yeah? Yes? Okay. At the same time, guys, see, I want you guys to remember this formula. That's it. Mass of solute in grams divided by mass of solution in grams multiplied by 100. This is going to give me what? It's going to be giving me the weight by weight percent of solute, or we call that as mass percent of solute, right? Or people, I can write it simply like this. See, mass of solute I'll be representing by W2. Mass of solution I'll be representing simply by W solution in grams multiplied by 100. Yeah, remember this as well. Correct? Okay. Now, guys, I'm not going to show you problems right now. I'll make you, these basic things clear to you first, then we'll be doing problems in general, okay? Understand. There is second terminology, guys, which is what we call as weight by volume percent. How do we define weight by volume percent? Weight by volume percent is simply mass of the solute present in 100 ml of solution. Mass of the solute present in 100 ml of solution. That's what we call as weight by volume percent of solute. Yes, right? So people, its formula is simply going to be weight by volume percent of solute will be equal to mass of solute in grams divided by volume of solution in ml multiplied by 100. Yes. Now you need to remember only one thing. See, I'm writing a statement like this. I'm writing 20% weight by volume, 20% weight by volume of NaCl aqueous solution. Of NaCl aqueous solution. What does that mean? It simply means 20 grams of NaCl. It simply means 20 grams of NaCl is present in 100 ml of solution. Is present in 100 ml of solution. Okay, I got the mass of solute, I got the volume of solution from this statement. So people, you should know how to decode these statements first of all. Okay, you should know how to decode these statements first of all. Yes, you should know how to decode these statements right here first of all. Okay, now guys, there is one more statement which I would like to share with you. What is that? That is volume by volume percent. Yes. What is volume by volume percent of solute all about? It's very simple again. Volume by volume percent is defined as volume of the solute in ml present in 100 ml of solution. Yeah. Volume of solute in ml present in 100 ml of solution. That defines the volume by volume percent of solute. Yes. So people, I'm going to write its formula. It's already written. Volume by volume percent of solute is always equal to volume of solute in ml divided by volume of solution in ml multiplied by 100. This is the simplest way by means of which we can define the volume by volume percent. Yeah. Now guys, I'm going to write a statement over here and I want you guys to decode this statement as well. I'm going to write 20% volume by volume of NaOH aqueous solution. Of NaOH aqueous solution. What does it mean actually? What does it mean actually? It simply means 20 ml of NaOH, 20 ml of NaOH is present in 100 ml of solution. Is present in 100 ml of solution. Very, very, very simple. Yeah. 20 ml of NaOH is present in 100 ml of solution. Correct? Right? Now guys, see. Now guys, see. Understand what I'll say. Understand what I'll say. I told you just now 5 minutes back, I gave you one relation. What was that? That was weight by volume percent of solute. Right? That was equal to mass of solute in grams divided by volume of solution in ml multiplied by 100. Correct? I'm going to give you one direct result which you will be using in the problems. What is that result going to be? Understand. See guys, for example, if the density of the solution is given to us, we can say density of the solution is mass of solution divided by volume of solution. Yes. So people, from here, can I calculate the volume of solution in ml? Yes. Volume of solution is going to be mass of solution divided by density of solution. Yes. Now people, can I put this volume of solution right here over here? Correct? So I can write something like this. Weight by volume percent of solute is going to be equal to W2 divided by volume of solution in ml. It's going to be mass of solution in grams divided by density of solution. So I'm going to write that density of solution over here. Correct? So people, what do we call this term if you remember? Should we call this term as weight by weight percent of solute? Absolutely. Correct? So should I be saying weight by volume percent of solute is equal to weight by weight percent of solute multiplied by density of solution? Yes, I can see that. That is one direct result which I'll be using in the questions. Yes, I'll always write weight by volume percent of solute is always equal to weight by weight percent of solute, weight by weight percent of solute multiplied by what? Multiplied by density of solution. I want you guys to remember this direct result as well, by means of which we can solve the questions fastly. Okay? Yes? Yes? Okay. Now guys, see. There is something called as mole fraction. What is mole fraction all about? As you all must be knowing, mole fraction of solute is simply defined as number of moles of solute, ratio of moles of solute divided by, ratio of moles of solute to the total moles present in the solution. Similarly, mole fraction of solvent, number of moles of solvent to the total moles present in the solvent. This is something which you all must be knowing. Correct? I'm going to directly show you its application part right here. Correct? See guys how this part is done. See guys how this part is written. This is something which you already must be knowing, right? Mole fraction of solute is equal to number of moles of solute divided by total moles present in the solution. Similarly, mole fraction of solvent is going to be number of moles of solvent divided by total moles present in the solution right here. Yes? Okay. See guys, this is the first and a simple question which is given to us. What is it? Calculate the mole fraction of solute in 10% weight by weight of NaOH aqueous solution, correct? What can I get from here? What can I get from here? First of all guys, I'm given with something called as 10% weight by weight of NaOH aqueous solution. What does that mean? That simply means 10 grams of NaOH. That simply means 10 grams of NaOH will be present in 100 grams of solution. Yes, 10 grams of NaOH will be present in 100 grams of solution. Yes. Now guys, understand, can I say I got the mass of solute? Yes, can I say I got the mass of solution? Mass of solute is represented by W2, which is given to me as 10 grams. Mass of solution is given to me as well. So mass of solution is simply 100 grams. People, I got two things, mass of solute, mass of solution. Can I get the mass of solvent as well? It's going to be 100 minus 10, which is going to be 90 grams. And what is my solvent right here? Solvent right here is water. Solvent right here is water, okay? What am I supposed to calculate? Mole fraction of solute. Mole fraction of solute. As you must be knowing, mole fraction of solute is equal to number of moles of solute divided by total moles present in the solution. Yes, so people, in order to calculate mole fraction of solute, you should know the value of N2, you should know the value of N1. Now the point is, how do we get the value of N2 and N1 right here? See guys, I can say N1 will be equal to number of moles of solvent will be equal to mass of solvent divided by molar mass of solvent. What is the mass of solvent? 90 grams divided by molar mass of solvent. Solvent is water, its molar mass is 18, so the value is going to be 5. So N1 value is 5. So people, similarly, can I get the value of N2? Number of moles of solute, it's going to be mass of solute divided by molar mass of solute. Mass of solute we got to know as 10 divided by molar mass of solute will be 40, as the molar mass of NaOH you all must be knowing, that is 40. So N2 value we got. So people, I got the value of N1, N2. So I'll put all these value over here in this equation. I'll get the answer as 1 by 21. 1 by 21 is going to be the mole fraction of solute right here. And people, remember at the same time, mole fraction of solute plus mole fraction of solvent for a particular solution is always equal to 1. Once you get the chi2 value, you can calculate the chi1 value as 1. 1 minus chi2, it is going to be 20 divided by 21. This is going to be the mole fraction of solvent right here. Okay, these were the two things which you were supposed to calculate from this question. Let me know in the chat box if it's clear to every single guy right here or not. Let me know in the chat box, guys. Yeah? Let me know in the chat box if everything is clear to everyone or not. Do hit the like button if you got it. Yes? What I simply told, mole fraction of solvent plus mole fraction of solute for a particular solution, that's always equal to 1. You got the mole fraction of solute from here. Just put the mole fraction of solute into this equation. You'll be getting the mole fraction of solvent, which is 20 by 21. That's it, yeah? Correct? Okay. All right, guys. Let's move on with something called as molarity. Let's move on with something called as molarity. What is molarity all about? What is molarity all about? Simple, guys, number of moles of solute divided by volume of solution in liters. Or first, let's try to define it. Number of moles of solute present in 1 liter of solution. That's what we call as molarity. Yes. Number of moles of solute present in 1 liter of solution, that's what we call as molarity. Absolutely. And its formula simply, guys, it's going to be number of moles of solute divided by volume of solution in liters. Yes. Or I can write it like this: molarity is equal to number of moles of solute divided by volume of solution in liters. This is going to be one formula by means of which we can calculate molarity. Number 2, I'm giving you, instead of N2, N2 is number of moles of solute, I can write mass of solute divided by molar mass of solute multiplied by volume of solution in ml multiplied by volume of solution in ml, and over here I'm going to multiply it by 1000. Yes, this one more formula by means of which we can calculate the molarity. Yes, correct. Simple, guys. Molarity is equal to number of moles of solute divided by volume of solution in liters. Or instead of N2, which is the number of moles of solute, will be equal to mass of solute divided by molar mass of solute. Instead of volume of solution in liters, I'm taking volume of solution in ml multiplied by 1000. These are the two formulas by means of which we can calculate the molarity of any solution right here. Correct? Number 1. Number 2, guys, I'm going to give you one more direct result, which is going to be molarity is equal to 10 multiplied by density of solution multiplied by weight percent of solute, weight by weight percent of solute divided by molar mass of solute. Yes. So remember this relation as well. This is going to be used in the questions directly right here. Okay, correct. Now people, one more relation. I told you one thing few minutes back. Weight by weight percent of solute multiplied by density of solution. Do we call it as weight by volume percent? Absolutely. Yes. So people, I will get one more relation for molarity, that is 10 multiplied by weight by volume percent of solute divided by molar mass of solute. Yes. Remember this relation at the same time. These are the few relations which will be directly used in order to calculate the molarity of the solution. Yeah. Very, very, very simple, correct? At the same time, guys, remember one more important thing. Molarity depends on temperature. It is temperature dependent, right? On changing the temperature, molarity changes. Remember it at the same time, okay? Himanshu, this is the English channel, bro. I'm not supposed to talk in Hindi, yeah? Okay, now guys, see. A very, very simple and basic question which is given to us so that you can get familiar with the formulas right here. See. Calculate the molarity of solution containing 80 grams of NaOH in 200 ml of solution, right? My solute, which is given to me as NaOH, correct? This is the mass of solute. That means this is the value of W2 which is given to me. Yes. What is this value? This value is the volume of solution in ml. What am I supposed to calculate? I'm supposed to calculate molarity. So molarity of the solution will be equal to W2 in grams multiplied by 1000 divided by M2 multiplied by volume of solution in ml. This is the formula a few minutes back I told you. W2 value, mass of solute, which is given as 80 grams multiplied by 1000 divided by molar mass of solute, molar mass of Na, which is 40 multiplied by volume of solution is 200. So you will be getting the value right here. How much? This is going to be 41, this is going to be 42, this is going to be 201, 205, 5 2s are 10. So molarity of the solution this will be 10. What does this 10 mean right here? I can say from this 10, this is the value of molarity, or I can say something like this. I can say 10 moles of solute is present in 1 liter of solution. Yes. 10 moles of solute is present in 1 liter of solution. Yes, very, very simple, correct? Okay, let's move on, guys. There is something called as semi-molar solution. That solution whose molarity will be 0.5, that's called as semi-molar. There is something called as decimolar solution. That solution whose molarity is 0.1, that's what we call as decimolar. There is something called as centimolar solution. That solution whose molarity is 0.01, that's what we call as centimolar solution. And that solution whose molarity is 0.001, that's what we call as millimolar solution. These are few important basic terminologies which I want you guys to remember right here. Yes, correct? These are few important basic things which I want you guys to remember right here, correct? Semimolar 0.5 solution, decimolar 0.1, centimolar 0.01, millimolar 0.001. Yes? Yes? Now guys, understand. Calculate the mass of NaCl required to produce 100 ml of semi-molar solution. This is the question which is given to me, yeah? This is the question which is given to me. Now the point is, how do we solve this question? Again, a very, very simple question, yeah? Again, a very, very, very simple question. Calculate the mass of NaCl. NaCl is my solute. I'm supposed to calculate its mass. That means I'm supposed to calculate the value of W2, mass of solute, correct? Few minutes back, I gave you the formula for molarity, which is equal to W2 multiplied by 1000 divided by M2 multiplied by volume of solution in ml. Yes, this is something which we know. This is something which we know, correct? Now guys, say semi-molar solution. Semi-molar solution means molarity of the solution is given as 0.5 is equal to W2 multiplied by 1000 divided by molar mass of solute. Molar mass of solute is my NaCl. Molar mass of solute is 58.5 grams per ml. Volume of the solution is given to me, I guess, yes, 100. Just solve this equation, get the value of W2 from here. That will be the answer, yeah? That will be the simplest answer, guys, correct? Yes. Okay. Now guys, there is something called as this thing I told you a few minutes back, yes? This thing I told you a few minutes back, molarity is equal to 10 multiplied by density of solution multiplied by weight percent of solute divided by molar mass of solute. At the same time, molarity is equal to 10 multiplied by weight by volume percent of solute divided by molar mass of solute. This is something which I told you a few minutes back, right? Now guys, see. I'm given with something written like this: 70% weight by weight of H2SO4 solution. The density of the solution is given to me. I need to calculate molarity. So simply, I'm not going to use my brain right here. I'm just going to use the formula. I just need the formula. I'm done. Yeah. I'll simply say 10 multiplied by density of solution is given to us 0.49. Weight by weight percent of solute is given to us 70. Divided by molar mass of solute. Solute is my H2SO4, I guess. Yeah, its molar mass is 98. Just calculate it. You'll get the value of molarity right here, which is done and dusted. Yeah. Correct? Very, very, very simple. Now guys, at the same time, there is something called as molality. But I think guys, we will stop right here because my throat just started paining. Yeah. Let's finish it right here. There is only few more topics left, which I'll be talking about in the coming days. Okay. That will just take 1 hour. Okay. 1 or more than, 1.5 hours, like that. Molarity of dilution and molarity of mixing. Yeah. Okay. Yes. So people, with this, we'll take a leave right now. I'll see you guys tomorrow. Not tomorrow. Tomorrow I'm on leave. I can say, yeah. I'll see you guys day after tomorrow. And day after tomorrow, we are going to see what? We are going to see the solid state. We are going to see the most expected JEE 2021 questions. Yes. So do not miss that session at all. That's going to be highly, highly, highly beneficial for you. So people, you guys take care. Bye-bye. God bless you all. Love you all. Yes. So stay safe. Good night. Bye-bye guys. Take care.